Let's talk about a new kind of computer. And I don't just mean a faster one. I mean a machine that's built on a completely different understanding of reality. A machine that doesn't just calculate, it rewrites the rules of what's possible.
And look, that's not me being dramatic. That's a statement of fact coming from the very edge of what's technologically possible. For all their incredible power, the massive supercomputers we have today, well, they're about to be left in the dust. And it's because they're running smack into a wall.
We're calling this the computational cliff, and it's exactly what it sounds like. It's that point where our very best machines, the engines that drive modern science, are hitting the absolute limits of physics, of energy, and of complexity itself.
So what's the problem? Well, it gets right down to the language these machines speak. Classical computers, the ones in your phone and in our biggest data centers, they use bits, zeros and ones. It's a binary, black or white view of the world. Frankly, it's a blunt instrument. But the universe doesn't work that way, does it? Quantum computers use something called qubits. You can think of qubits as speaking nature's native language. A qubit isn't just a 0 or a 1. It can be a 0, a 1, or both at the exact same time. And that lets it explore this incredible, vast landscape of possibilities all at once.
And then there's the power bill. You see this number? 20 to 30 megawatts. That's how much energy a single top-tier supercomputer, like Frontier, needs to run. That's enough to power a small city. We just can't keep going down this path, building bigger and bigger machines that need their own dedicated power plants. That whole strategy has hit its limit.
And here's the kicker. Even with all that city-sized power, we're still just too slow for the problems that really matter. You want to screen molecules to find a new drug? That takes months. You want to run a really accurate, high-resolution climate model for just a couple of centuries into the future? Our best supercomputer today would need, literally, millions of years to do it. We're not just slow, we're hitting the speed limit imposed by reality itself.
So what if we just stop trying to brute force the problem with classical bits? What if we build a new kind of machine? That's exactly what's happening. The solution is to fuse two of the most groundbreaking technologies of our lifetime into something completely new.
And this is it. It's called a quantum AI hybrid cluster. It's a totally new way of thinking about computing. It takes the incredible pattern recognition abilities of AI running on classical chips, like GPUs, and marries it with the mind-bending calculation power of a quantum processing unit, or QPU. The result? A machine that can solve problems that were completely impossible for either one to handle on its own.
So how does this thing actually work? Well, you can think of it as having three layers. First, you've got the classical brain. That's a massive AI supercomputer that does all the prep work, getting the problem ready. Then, when it hits a part that's just impossible for a normal computer, it hands that piece off to the quantum oracle. That's the QPU, and its job is to do the magic. And tying it all together is the smart conductor, a layer of software that's like an incredibly intelligent traffic cop, knowing exactly which tasks to send to the classical side and which ones need the deep power of the quantum core.
Now, it's really important to understand, this isn't about quantum replacing classical computing. Not at all. It's a true partnership. It's a symbiotic relationship where each side makes the other exponentially more powerful.
I absolutely love this analogy. Think of the AI as the savvy, brilliant manager. It gets the project ready, it takes the results from the quantum processor, which can be a little messy and noisy, and it cleans them up and it steers the whole operation. The QPU, the quantum processor, that's the brilliant but maybe a little temperamental artist. It's the one that performs the act of pure creative genius, solving that piece of the puzzle that is just flat out impossible for anyone else.
Okay, so we have this amazing new machine. But what's the big deal? What can it actually do for us? Well, this is where things go from theory to reality. And believe me, the impact is going to be absolutely world-changing.
And I want to be crystal clear here. We are not talking about small incremental improvements. The early systems that are up and running are already showing speedups of 100 to 1,000 times on real-world business problems. That's not just a step forward. That is a gigantic leap into a new era.
So what does that look like? In medicine, it means simulating how a new drug will interact with a virus in just a few hours, instead of months. It means we can actually hunt for cures to things like Alzheimer's and cancer inside a computer. And it goes even deeper. We could design, atom by atom, brand new materials that we can only dream of today, like superconductors that work at room temperature or special catalysts that can literally pull carbon right out of the air. The periodic table basically becomes like a set of building blocks for us to shape.
This level of precision is going to completely change how we see our own planet. We'll be able to create climate models that are so detailed, down to 100-meter resolution, that we can finally see the dangerous tipping points that, right now, we are completely blind to. And that exact same power can be turned to our global economy, optimizing massive supply chains in seconds or pricing complex financial instruments almost instantly.
Okay, but with this kind of reality-bending power, you just know there has to be a catch, right? A downside? And there is. This isn't just a story of incredible promise. It's also one of some very real peril.
We have to get our heads around this. We need to stop thinking of these machines as just tools. One of the sources for this explainer put it perfectly. They are new organs of collective intelligence. And when you think about it that way, everything changes.
First of all, let's talk about the cost. Because, wow, a single one of these hybrid clusters costs over $1 billion. It needs an entire facility, with massive cryogenic refrigerators to keep the quantum parts colder than deep space. So for right now, access to this kind of power is limited to a few governments and a handful of giant corporations.
And this concentration of power creates this incredible double-edged sword, especially when it comes to cybersecurity. The very same machine that can shatter all of our current encryption standards can also be used to create new, unbreakable post-quantum cryptography. The power to design cures for diseases is mirrored by the power to design new pathogens. This means that having careful democratic oversight isn't just a nice idea, it's an absolute necessity.
But look, we've seen this movie before, right? The very first general-purpose computer, ENIAC, filled an entire room. Decades later, the smartphone in your pocket is thousands of times more powerful. The same thing is going to happen here. This immense power, which is right now locked away in these billion-dollar labs, will eventually compress. It will become accessible.
So make no mistake, these machines are being built as we speak. Right now, somewhere, the refrigerators are humming, cooling things down to near absolute zero. The qubits are being tuned and entangled, getting ready to calculate our future. And all of that leaves us with one final, unavoidable question.
Will we be the ones to steer this incredible new power, or will we simply be steered by it? The choice, at least for now, is still ours to make.